In this video, we're going to define and discuss the interior of a set in a topological space. So here's our definition. If x tau is a topological space and A is a subset of x, then point x is an interior point of the set A if there's an open set U such that x is in U and U is a subset of A. In other words, x is an element of U, which is a subset of A. So that there must be some open set containing x that is completely contained inside of A. This is the same definition as what we had for a metric space. So same definition as in metric spaces. And that means that everything that we had previously will carry over from the realm of metric spaces to the realm of topological spaces in terms of the interior of a set. It only relies on the definition and the idea of open sets, which is the same. Some more language. If x is an interior point of A, we say also that A is a neighborhood of x, and also the set interior of A int A is the set of all interior points of A. So int of A is a set. And it's by definition, the interior of A is a subset of A because the interior of A consists of elements that are inside of A. Here is a theorem stating several facts about the interior of a set in a topological space. So first, the interior of A is the union of all open subsets contained in A. And we can see that if x is in the interior of A, then there's some open set U sub x that is contained inside of A, and therefore that entire open set, again, is inside of A, and all of its points are in the interior of A. For any other open set that's contained inside of A, U sub y, all of its points are in the interior of A, and so on. So the union of all these open sets is going to be equal to the interior of A. And therefore, it's also the case that the interior of A, whatever that is, interior of A, is the largest open subset that is contained in A. So this is interior of A. It's the largest open subset contained inside of A. So we already proved that previously when we talked about the interior of a set in terms of metric spaces. Similarly, we proved that a set A is open if and only if A is equal to the interior of A. We proved this. If A is a subset of B, then the interior of A is a subset of the interior of B. We proved this as well, all in the context of metric spaces, which does, again, carry over to topological spaces in this case. Everything in terms of open sets is defined the same way, as well as the interior. Lastly, the interior of A intersected with B is equal to the interior of A intersected with the interior of B. This one we haven't proved yet, so let's prove it. So our claim is that these two sets are equal. In order to prove set equality, we can prove that each set is a subset of the other. So to show the first inclusion, observe that A intersected with B is a subset of A. So note that A intersected with B is a subset of A, and also A intersected with B is a subset of B. So now, by 3 above, we know that if one set is a subset of another, then the interior of the first set is a subset of the interior of the second. So the interior of A intersected with B is a subset of the interior of A, and the interior of A intersected with B is a subset of the interior of B. So that means that the interior of A intersected with B is a subset of each of those things. Therefore, in the intersection of them is a subset of the interior of A intersected with the interior of B. Now for the reverse inclusion, Let's see. So both int A and int B are open sets. So observe that the interior of A and the interior of B are open sets. This is basically, again, by definition. We could also note that, part 2 of the theorem above says that A is an open set if and only if A is equal to the interior of A. So that would also give it to us. So since those are open sets, therefore, any finite intersection of open sets is open. So the interior of A intersected with the interior of B is open. And so this is an open set, and it's also a subset of the interior of A intersected with B. It's a subset of A intersected with B. Interior of A intersected with interior of B is a subset of A intersected with B. How do we know? Well, clearly the interior of A is inside of A, the interior of B is inside of B, so the intersection of those two things is inside of A intersected with B. So it's an open set, it's a subset of A intersected with B, therefore, because int A intersected with int B is an open subset of A intersected with B, we then know that interior of A intersected with the interior of B is a subset of the interior of A intersected with B. So we've proved that each set includes the other, and therefore the sets are equal. Note, we didn't state sort of a similar idea. We didn't state that the interior of A union B is equal to the union of the interiors. And that's because this is false. This is not in general true. So as an example, let's consider the usual topology on R. In other words, the topology given by the usual metric, distance between A and B is the absolute value of A minus B. This gives us open intervals as open sets and all unions of open intervals as open sets. So this is generated by the usual metric. So let's consider the sets A equals the closed interval from 0 to 2 and B equals the closed interval from 2 to 4. Let's look at the interior of A union B. The interior here of A union B would be the interior of now the closed interval from 0 to 4. That would just be the open interval from 0 to 4, the largest open set contained in that closed interval, whereas the interior of A union the interior of B would be equal to the interior of A is the open interval from 0 to 2, union the open interval from 2 to 4. And we see that these two sets are not equal because 4 is in the interior of A union B, but 4 is not an element of the interior of A union the interior of B.